tiny rods, and it's actually this big particle swimming in the sea of tiny rods. Okay, it's important to think about it. Well, people do also other scales. I'll show today that we can go sub-micron, we can go to 100 nanometers scales. You can actually go to 50 nanometer, 10 nanometer, 5 nanometer particles. And ICAM students, I know, I think on the last day you heard here, I'm sure, an excellent talk by Thorsten Hegman, where he really puts nanoparticles, where you have really this object in here, I say of 5 nanometers in size. Okay, but these systems are very different. Okay, so for us, it's now important to see that we have big objects in a sea of small objects, in a sea of these tiny little rods. And just to show you that one can really use very diverse colloidal particles, these are some systems we looked at in the past. So they can be micro rods. You can actually functionalize surfaces of particles. In this case, this black part, you can put a patch of gold on one side. And that's maybe one other interesting thing which we've started to work on. So actually, particles can change shape. Okay, so you actually change. In this case, I show you the simple example where you have a sphere and you actually change it in the ellipsoid. And things change if you change the shape. Okay, the assembly, anyone who works with colloids will know that the structures which you see, interaction potential, they strongly depend on the actual shape. Okay, not to say that one could actually perhaps change topology. Now, the main interest in looking at liquid crystal colloids is because they have some special properties. Okay, something what I might call advanced material characteristics. Okay, and here I give you just some selected examples. The first, I think, motivation for looking at liquid crystal colloids came from the fact that they can self-assemble. This is one of the early works from Ludé and Poulain, okay, building on this. Now I probably can only say classical work by Poulain, Weitz, Stark, and Lubinsky. Okay, and what you see here, you see these tiny dots. Okay, these are actually droplets. These are oil droplets. I think it's glycerin. Okay, glycerin droplets. And what's special about it, they form chains. Okay, this would not happen if this surrounding fluid was isotropic. Okay, this is because it's kinematic. They form these nice chains. This is our work now from already quite a few years back. Okay, and here by using laser tweezers, we actually show now you have solid particles, and we show that we can make them actually in a very regular two-dimensional structure. Now, this is a work from the group of Tanaka from Tokyo and Bellini from Milan, University of Milan. And what they look at here is actually that they create such closed pack arrangements of particles. You can say they can create templates. Some people might call this opals, colloidal opals. And what's special about them, when they put liquid crystals, the nematic liquid crystal in, they see a complex conformation of defects, okay? I hope you see it. So just this complex lattice of defects. And now what they do next, they apply external fields. And when they apply an external field, they imprint into the material a very distinct structure, and even when they remove the field, this structure remains there. Okay, so this is a clear signature of memory. So actually, by imprinting conformations of defects into this, you can create memory states. Okay, this is one interesting example from the literature from the past years. Okay, this is also a result from 2 years back. Okay, so I hope you see this. Okay, here again, we are looking at colloidal particles, and I hope you can see these darkish lines going around the particles. Okay, so these are disclination lines, defect lines. Those who know more, it's -1/2 disclination lines. And actually, what we show in this paper here is that we can tie arbitrary knots. Okay, by taking an array of particles, we can tie arbitrary knot. And actually, what we want to say a little bit further. So you tell us the knot, and we can make it. Okay, so we can actually go the reverse direction, not just see what we got. This is a work from the Edinburgh group. So Mike Cates and Mario Duzza and co-authors. Okay, so what's special about this system is that actually they observe non-Stokesian microrheology. Okay, so when you compare the force with the velocity, it's very different as if this was an isotropic fluid. In this case, it's a cholesteric. Now, this is a work from Smalyuk team. Okay, and what's special about here is they actually see that the particles can really change shape. What they're using some very special particles, actually nematic liquid crystal elastomers. We had a whole session yesterday on this type of materials. Actually, what they do when they're shining with a laser beam on some spot, okay, the particle can change shape. Yeah, can change shape, and there are different things. And so this is a phenomenon which you might call active shape morphing. Now, to give some motivation for now from photonics perspective, okay, what can you do actually if you use colloids and liquid crystals? What a special phenomenon. Again, I'll give you just a few selected examples from the literature. So this is work from Laurentovich group, okay, from Kent. So what you see here is a capillary. Okay, it's actually a capillary filled with golden nanorods. And in here, okay, you see this electrode. what they can do, if they apply the right field, actually they can make this central electrode disappear. Okay, and if you want me now to use sort of a bit more popular language, you call it, it becomes invisible. Okay, becomes invisible, and that's a sign, this might be called a tunable transformation optics. Another recent example by Liu and co-authors. Okay, so what they here do, actually, they can create, now what they use is polymer dispersed liquid crystals, okay, and by shining with 5 beams, they take 5 laser beams, they create an interference pattern, and they imprint this interference pattern into the polymer dispersed liquid crystal. So polymer dispersed liquid crystal, it's a mixture, if you say it's a mixture of polymers and liquid crystal. And what they get is actually a structure which is a 2D Penrose lattice, and this lattice turns out that can work as a very good low threshold lasing material. Okay, just to give you an example. Okay, what kind of materials can do. Actually, I'll go to Penrose lattices later on. Now, 2 examples from our side. Okay, this is a work we did a few times ago, and what you see here is a pneumatic droplet. Okay, just the simplest pneumatic droplet which you see in every textbook. Okay, you recognize this radial profile. Okay, which is embedded in a polymer. And actually, what these droplets can do, they can act as resonators. And what's special about these resonators is that they are highly tunable. So what you do, you shine with a laser into the droplet, and what turns out is that this light starts to sort of circulate around the droplet. To be more precise, what happens is that whispering gallery modes emerge in such droplets actually by changing the profile of the pneumatic droplet. Okay, you can do this, for example, with external fields. You can change how this light circulates in a droplet. Okay, maybe now a recent example. So this is really a work by Miha Ravnik. He's sitting in the audience. You should talk to him. Okay, it's his work. Okay, so what we're looking at here is actually propagation really of light fronts. Actually, what we want is to change and mold light fronts by using distortions of a liquid crystal. So this is just, in this case, this is a SMECTIC A waveguide, okay, with this distinct radial profile. Okay, and you can do interesting things just by saying, going in with the Gaussian beam, things change quite nicely. Okay, so this brings me to the outline of the talk. So I'll start by theory and modeling approaches which we use to study the systems, and then I'll go on to 3 structures. There are 3 sets of structures, which I think have interesting applications also in the direction of photonics. Now, we all know that liquid crystals can be described with a quantity. Also, students, you had, I think yesterday, a whole talk on Q tensors. Okay, you know a lot, probably more than I do. Okay, so actually you can characterize liquid crystals by a quantity called the order parameter tensor. And if we remember, this n is the director, the average orientation. This s characterizes the fluctuations, and these fluctuations around the director of the molecules can be asymmetric, and it's characterized by axiality. Okay. Now, if you're interested also in the true dynamics, you need to think about the flow and also density, because we're thinking about fluids, okay? Now, in order to approach the structures, various structures, colloids in liquid crystal, at this micrometer scale, a very strong approach is to use free energy modeling. And we use this for a long time, okay? Okay, a long time. And actually, there are 3 basic ingredients which you need to put in: the elasticity, the order, okay, the Landau term, and also this particles need to couple with the liquid crystal. Now, I kept asking why you use this approach, okay? And well, one major advantage of this approach is that can be quite easily extended for any other mechanisms which you might want to include, okay? Because someone might ask you, well, what happens if you put an external field? Can we look at the effect of flexoelectricity? What happens if you do chirality? Well, if the materials become biaxial, okay? This kind of phonological approach is really excellent for this kind of combined effects. Another advantage, which I think is important to realize, is that, well, maybe not just with just single elastic constant approximation, but if you include 3, you can achieve, if you work hard and do things right, you can even achieve quantitative agreement with experiments. I think that's important, okay? That's important. So this is what even this approach is good to think about. Okay, this free energy, right? You know, free energy, if you want to find a stable configuration of states, needs to be minimized. Okay, it needs to be minimized. You do this with the Euler-Lagrange algorithm. Actually, and then this algorithm, which we eventually use, is the relaxation algorithm. Now, again, it's a process we used in the past years a lot. Okay, now, but again, I keep getting questions. Why do you use the relaxation algorithm? So, what do you say? You just describe sort of a diffusive dynamics to your system. Well, the reason is that this dynamics mimics the real dynamics of the system. The only thing you're neglecting is material flow. Okay? So you can solve these equations with any other solver. There's many ways. Okay? There are many other methods which you might say are more advanced and they can do other things. But here you get for free sort of the roughly correct dynamics of your system. And sometimes these trajectories tell you a lot about the actual properties of your system. Okay? Okay, and we do apply these systems on a cubic mesh, and so on. And when you end up, you get an equilibrium structure. Now, we can also do dynamic simulations. So if you really want to think about flow, things flow in channel, or you sort of material moves. Okay, in this case, you need to apply hybrid lattice-Boltzmann algorithm, something I work on with Julia Young at Oxford quite a lot. But this will be a separate talk, okay? Now, if this is sort of how we get the structure, now, how can we sort of how can we actually turn these structures into sort of photonic materials, or how can we characterize them from the photonics perspective? Well, the first thing, maybe you'll say it's trivial to realize, is actually that this knowledge on the order parameter tensor, which we have, actually directly corresponds to the electric tensor of our system. So something what in more loose language you might call sort of birefringence of your material. Okay? There's a direct one-to-one correspondence. Okay? And as soon as you get that, well, we're thinking about photonics, so how light electromagnetic beams propagate, you need to write down Maxwell's equations. And here I show you just written down in one formulation where we already assume no charge, no current, and the material is magnetically, sort of from magnetic permittivity, isotropic. Okay? These are, I think, quite reasonable assumptions, but we can talk about them if you have questions. Okay? Maybe, and the thing to realize when you write down this Maxwell's equations is that, you see, you have this epsilon, okay? This is our dielectric tensor, and what's really important, and this is something what we want to use, is this epsilon changes in space. That this dielectric profile, the electric tensor, or if now you can think about liquid crystal profile, they change in space. So they are functions of space, and you have it here and here, and this this makes solving this equation a little bit harder, okay? A little bit harder. Okay, now, the thing we want to do now, okay, we've written down the Maxwell's equations, we want to think about photonic bands, okay? We want to think about whether our structures can act as photonic crystals. And to do so, okay, you assume one frequency, you end up one frequency of your field, then you rewrite these equations, eventually turn out something like this, okay? And then you need to solve this in a particular periodic medium. So what you know, and there's a method which is well established in the literature. So the block plane wave expansion. Actually, I would like to point out here this paper by Honer, Stickman, and Sommers, okay, where they actually thought in this direction. Okay, so we follow their ideas, their ideas. But actually, this approach is very well known. If you do, I'm sure you all thought about and had to learn about bands in semiconductors. It's exactly the same approach. Okay, how to calculate electronic bands in semiconductors. It's exactly the same problem. Okay, and what end up with, when you rewrite this equation, what you realize is you need to solve a set of linear equations. You need to find out, it's an eigenproblem. It's an eigenproblem which you need to solve, and then we can do this with standard functions from Leibach. And things could be optimized and so on. There's a lot of, one could go further here. Okay, so eventually what you need to do is sort of Fourier transform of this inverse dielectric tensor, and then numerically solve an eigenproblem. That's sort of if you want to get bands. Now, but you can ask a different questions, okay? You can ask a different question. We still have our Maxwell's equation. We still know that we have a profile of our structure, but you can actually ask a question. I want to study a different problem. Actually, what I show you here in this yellow, I want to say this is my liquid crystal. Okay, it has a complex profile has a complex profile, so the molecules change direction and so on. And I put light sources into my material. Okay, so they can be such droplets or such spots. Actually, they can be lines. Okay, you can imagine attaching fluorescent dyes to such points or source of material. And my question would be, how does light propagate in these materials? Okay? What do you get if I turn on these light sources? Okay, these light sources. And in order to do so, the strong approach is to use finite difference time domain calculations. Finite difference time domain calculation. That's again, it's an established approach in isotropic materials. Here, it's a little bit more tricky because it's really this epsilon is a function of space. So you have to think hard, okay? And again, I'll point you, it's work of Miha Ravnik. You should go and talk to him. Okay? Okay? You need to think about properly how to allocate lattice and so on. Okay? There are things there are tricks to consider. Okay, so this is sort of the methods we can use. Yeah? But now, let's go to examples of structures. Okay, and the first one I want to speak about is 3D nematic colloidal crystals. Okay, and I'd like to start with this. So you see just a simple particle, and everyone who worked with colloids will immediately recognize that it's actually this particle, and there's a -1 hedgehog sticking into it. Okay, and this is actually called an elastic dipole, right? Everyone who worked with colloids knows that. Okay. Well, of course, you also know that if these particles become small, or if you reduce their surface anchoring, or if you put external fields, well, of course, this point defect can change into a ring. You get Saturn rings and so on. These things can happen. Okay, but I want to stay in the regime when, say, particles are large enough such that we have these point defects sitting next to them. I want to have elastic dipoles. Now, but as soon as you realize you have the elastic dipoles, well, you also remember that elastic dipoles behave very similar to sort of magnetic or electric dipoles. Okay, when you have that, well, you can start thinking about how to build your structure. And what you know that the dipoles do, they like to form chains. Okay, and this elastic dipoles do just like this. Okay, so you can get dipolar chain. Actually, what they can do, they can also align in the antiparallel directions and build a cluster. There's also something they can do. Okay, so these are sort of two bound states, if you want, of a pair. Now, and well, this is exactly what we used in building the two-dimensional crystal. But as it turns out, you can actually generalize this to build, you can think about this exactly same lines to build now a 3D structure. 3D structure, and this basic element which you need to think about are dipolar chains. Okay? Here I have two. Think about I have a longer chain. Okay? And what I do next, I put it into a cell, and actually the stable structure of these chains tends to be an antiparallel stacks. So what I show you here is a unit cell. Is a unit cell of a 3D colloidal crystal. It's periodic, okay? It's periodic, and what I try to show you, so these blue ones, these are sort of the elastic dipoles pointing up, okay? And you know, pointing up, whereas the central guy points in the up and down direction. And actually, these chains I was mentioning, right? It's a periodic cell, so you should imagine there's the red guy, he's sitting here, further up and further up, with the blue one, so on, okay? It's a periodic cell. So you have antiparallel chains sitting in such actually tetragonal unit cell basis. So you have two particles per unit cell. And this structure turns out to be stable. Well, but going from this numerical prediction, actually, these things can be realized in experiments. So what you see here, so this is a work from Mushevich lab, okay? So what you see here is particles, okay? They are 4 micrometer in diameter. They have strong homotropic anchoring, okay? Strong homotropic, so perpendicular anchoring at the surface. I actually have them in an isotropic cell, in a homotropic cell, this thickness. So, and this is a top view. So what you're seeing, so the cell goes in, okay, into the plane, and now you see actually a 3 by 3 crystalline. Okay, and that's a structure which you can make. The process they use is sort of really manipulating systems with the optical tweezers. It's actually at the border, to my opinion, between science and art. Okay, because you need to know things right, how to approach system and actually do the right sequences to build to avoid some internal torques. But actually, it's a structure you can make. Okay, now that you have a structure, okay, you can ask, does it have some interesting properties? Okay, and I think there's the first thing which you realize is actually if you put such a crystal, okay, you see here, okay, this guy is 4 by 4 by 3 in depth, I think, okay, and if you put it into an external field, which points like inward into the plane, okay, into the plane, what happens is that this crystal shrinks, and you see changes in the lattice constants of several tens of percents. Okay, and in the literature, this can be called a giant electric restriction. So this is a large change in the lattice constant, but there's an important condition. Okay, this works only if the dielectric anisotropy of the material is positive. Okay, the dielectric is positive, so it means that if you have your director, if you have your field direction, the director wants to align along the field. Okay, this is positive dielectric anisotropy. And I'm sure I don't need to remind you that changing the lattice constant will directly affect any photonic or light transmittance, photonic bands, anything in this kind of structure. Okay. Now, if the material, however, you can build the same material, the same structure, also in a liquid crystal with a negative dielectric anisotropy. You take a different liquid crystal. Okay. And this is now a side view. Okay. So this is now top. Okay. This is a side view. Actually, what happens here is that this structure rotates. Okay, if you now apply an electric field, see, 0 volts, some volts. Okay, the structure rotates as a whole, and it rotates by angles of several tens of degrees. Okay, so this is, you can call this electron rotation. And actually, the symmetry, the rotation axis depends strongly on sort of the edges of your crystallite. Now, this is sort of one family of structures which you can think about. Okay. Now I want to show you a different one, and the conference audience here, this nice talk by Professor Cates already about 3D blue phase colloidal crystals, but I want to go a bit further. I want to put them as photonic crystals, okay? Now, blue phases, okay, for those of us who are not entirely familiar with them, okay, so now I'll change the material. I'll not use anymore a nematic, but I want to use a chiral nematic. Actually, a chiral nematic with quite a strong chirality. So you need to put either dopants or the molecules themselves need to be chiral in order to get this chirality into the system. Now, the thing they do, the chiral materials, you know, they twist, okay? They twist. However, if they want to twist hard, actually they start sort of twisting in 3 directions, and you get phases which are called blue phases. There are 3. The third one is actually, it's amorphous, and we had a nice talk by Professor Cates. I'll stay there, okay? But actually, 2 phases have very interesting properties, the blue phase 1 and blue phase 2. They are fluids, but they actually have a unit cell, okay? You have an oily material which has a unit cell in terms of the orientational profile of the material. Okay? And that's a special property, and actually here I show you this pattern of the blue phase 1 and blue phase 2. So how to recognize them is with these distinct defect lines. Okay? They're very special because everything twists. Now there must be regions where you get a defect, and this is actually distinct patterns of the blue phase 1 and blue phase 2. This is the unit cell, and the scale, what you should visualize, this is sort of 300, 400, few hundred nanometers. Okay, this is sort of the size of this unit cell. And these phases have special properties. They switch very quickly. And maybe just for me, I think soon you will have a special session on this. So you'll hear a lot. Other people know some things. Okay, already know things. So maybe just but still to explicitly put it, this interest for the blue phases now comes from the fact that the Coase group was able to achieve materials with wide temperature range. Okay, they can do it really in 60, 70, I don't know what's the record now, it's high, right? Or wide temperature range. And another way to approach this stabilization of the phases was demonstrated by Kikuchi by doping these materials with polymers. What happens is that the polymers get stuck to these lines. Okay, so this is the interest for blue phases. Now, why we want to use the blue phases is actually we want to build a colloidal structure. Okay, that's what we want to do. And what I show you here is actually, again, okay, you see the red lines, these are our defects, but actually what I show you in green is local free energy density. Okay, and what does this green area show you is actually that if this local free energy density is high, this is where the particles want to go. Okay, so actually get regions in this phase which want to trap the particles. And since these phases are periodic, you have unit cell, these trapping regions are also periodic in space, and you might expect that actually colloidal structures will form. Okay, there are some examples. Okay, and it's really sort of the common. Yes, this was really done with weak anchoring in terms of what we heard at the conference. So these structures can be distorted. So we initialize them by putting particles close to the sort of now equilibrium spots, and then finding the local minimum. Of course, this would be very different if you just put them into a line and see how do they sort of form the structure. Maybe a suggestion, right, we put in our paper is that actually to really get such regular structures, you could grow particles in situ. And what do I mean by that? Okay, do you remember when I showed you the first nematic motivation slide by Ludé? Okay, when they got this oil droplets in chains, okay, actually what they did there, they did a phase separation. Triggered a phase separation in their system. So they had a nice dispersion of liquid crystal and oil. Actually, they figured phase separation, these droplets grew of optimal sizes in the right spots. Maybe you could do the same thing in blue phases. It requires, you need smart chemistry, good experiments. But that's sort of a suggestion which we're proposing in the paper in order to really get regular structure, okay? Now, okay, so this is, say we can build this structure, but now how would such a structure respond? So act as a photonic crystal. Now, photonic crystal, to remember, okay, you need a periodic modulation of the dielectric constant, or in this case, the dielectric tensor, at least in some direction. But there's one subtlety about photonic crystals, is that actually that the structure of photonic bands, so this somehow tell you how the light behaves in these materials, okay, it's crucially determined by the symmetry of the material. So if your material has a BCC lattice, does it have a FCC, so body-centered cubic, face-centered cubic, simple cubic, some other symmetry? Of course, you can tune these bands then with the other material parameters, but that's an important element, okay? And so here I'm citing a paper from the literature where actually they show if you have a diamond lattice, actually they have a diamond lattice of such, actually they need truncated tetrahedra positioned into a diamond lattice in order to achieve really a nice and a wide photonic band gap. Okay, so this is really, right? One needs to think hard how to engineer this material to achieve strong responses. Now, okay, so but what our materials can do, actually, I want to say that there are actually two symmetries effectively in our system. And what do I mean by that? So actually, the blue phase 1 or the blue phase 2, they have their own symmetry of the phase. So the blue phase 1 is a BCC symmetry, okay? It's a body-centered cubic, whereas the blue phase 2 is a simple cubic. But now when you add particles, actually it turns out they go into an FCC lattice, okay? So there's somehow a competition between FCC and BCC, and here actually you have a BCC versus a simple cubic. There's a simple way so how to change the role of either of the two, right? You can just change the material. Yeah, you can change the sort of vary the material parameters. And what do I mean by material parameters? Yeah, you can just simply change the particle size. Okay, if the particles are small, the material should respond as a blue phase photonic crystal. But if the particles are large, the material should respond as a colloidal crystal, ignoring the blue phase. Okay, so you have a two intermediate regime, and this is sort of it's a very much work in progress, and I'll show you just first result. But this is sort of one of the ideas which we're going. Of course, an important element is also changing the electric contrast and so on. Okay, what did I do? Okay. Now, this is now a calculation of photonic bands in a blue phase 1 FCC colloidal crystal, so this structure. What you see here, okay, this dark lines, okay, is just a structure with particles, and an isotropic, it's the upper ones, okay? Yeah, and then you have the blue phase 1. And I should say that this photonic bands were actually calculated by Honreich et al. In their paper, and we can perfectly reproduce the results. Okay, reproduce the results. Actually, the green guys is actually when you have both. Okay, when you have blue phase 1 with particles, actually this structure. Means we want somehow to dissect the effects of the two. Okay, and maybe I won't go very exactly into band gap structure, into the photonic band structure. Maybe just to say is that what we see is that by adding particles and changing the size, we can start opening some local band gaps. We don't see formation of full band gaps, okay, but local ones, and for sure we can change the size or the width of the band gaps by adding the particles. And actually, similarly seen also in blue phase 2. Okay. Now, this is sort of what you can do sort of from a photonics perspective. Now, this last third bit of structures, I want to show you tilings. Okay? And what the question I want to ask here is, actually all the colloidal structures I've shown to you, and which you usually see in the literature, okay, they have crystalline symmetry. Okay? And what do we mean by crystalline symmetry? Okay, they have unit cells. Yeah? They have unit cells, and here I just list some examples from the literature. There's a lot. Okay, there's a lot of them, but they all have crystalline symmetry. Okay, now the question I want to ask is, can I get a quasi-crystalline symmetry into my system? And quasi-crystalline, what I mean by quasi-crystalline is the system has, say, a 5-fold, a 7-fold, or some other complex rotational axis. Okay, now what do I want to do that? Right? There's a clear reason why I would like to do that. Well, perhaps thinking from the photonics perspective. Okay. Here, I show you an example from the literature, an excellent paper, okay, where they actually show when they get a 12-fold symmetry axis into the material, okay, this is one of the quasi-crystalline symmetries, okay, they can actually see opening of a full band gap in the material. Just by getting the symmetry axis in the material, you're sure that you will get a full band gap. I think that's that's an interesting idea, okay? Okay? And actually, and this is something we would like to do, okay, in some sense. And how we want to proceed is by using colloidal platelets. Now, why platelets? Okay, because platelets, what are platelets? Okay, here I show you immediately an example. This is work from Smalik team. Okay, what they show, actually, what you could visualize, right, that you have particles of the complex shapes, right? It has, say, 7 corners. Can I get a seven-fold symmetry axis in my system? Right? This is sort of an idea you have. And this is, okay, this is an experimental work, an excellent experimental work, okay, where you see they tried particles of various shapes, triangles, pentagons, and then squares with holes and without holes and so on. And we did some modeling along this direction as well. Okay, and actually, it turns out that what these materials do, well, of course, they can do amorphous structures. Yeah, you cannot get, yeah, this can happen. But if you try hard, well, maybe the structures you can get always have a unit cell. Okay, they build a unit cell. Yeah? So you have, again, a crystalline structure. And so it doesn't work directly, but there's a trick. Okay, there's a trick. So in order to achieve quasi-crystalline tiling, you need to combine the shape of the particles and also design the surface anchoring on the tiles. Okay, and what I mean by that, okay, so actually the tiles which we'll be using are pentagons, and what we will do, we will impose surface anchoring on top and bottom surface of my tile. Okay, this is you see the geometry. It's a planar cell. It's a layer of thematic. Here I'll have my tile. Okay, and what I'll do on top and bottom surface, I'll put uniform anchoring. So that means not degenerate. Okay, uniform. But actually the top and bottom surfaces must misalign. Will be misaligned. Okay, they will be at some angle. Okay, one with respect to another. And here I have some magic number 36. It can be also some other. Okay, it can be also some other. But they shouldn't be along some of the symmetry directions. Okay, some directions are forbidden. Okay, are forbidden. Okay, and these are the structures which I'll show you actually can build a Penrose P1 tiling. Okay, if you take this kind of, if you can Penrose P1 tiling, and that's a material with quasi-crystalline symmetry. Now, okay, we want to build structures. The first thing you always ask is what's the pair potential? Okay, so I have a pair potential between 2 platelets. Okay, actually it turns out there are 3 stable configurations, 3 stable. So one is stable and 2 are metastable. Okay, but that's not important. So important for us, which is the metastable ones. But so these are the bound states. But what's also important is that when if you rotate this guy at some other angle, which sort of is rotationally unstable, still it's bound in the lateral direction. This turns out to be crucial if you want to get really a tiling, a stable tiling. Okay. And now, if I speak sort of more loose, effective language, okay. So what you do by assigning the anchoring I spoke about, you actually get particles to get sticky edges in some sense. Okay, sticky edges. And the other thing, what these sticky edges do, they prefer edge-to-edge alignment. Okay, they don't want to misalign. Okay. And this is very different as compared to, say, geometrical tiles, where you don't have any potential. Okay, this is a bonus which you get. Okay, so these are sort of the ingredients which you realize are crucial when you're constructing this pair potential. Now, to build a Penrose tiling, actually there are 2 ways how to think about Penrose tilings. Of course, you cannot think about them. You cannot just take a unit cell. It doesn't exist. Okay, there's no unit cell. But actually, one way to think about them is actually to think about elementary building blocks. And what you see here is 3 colloidal clusters. Actually, they're called rhombus. Okay, you see the rhombus, the boat. You see the boat and the star sitting here. Okay, and as it turns out, they're stable. Okay, they're stable, and now they're stable. And having them, actually, just by taking this cluster, you can build the whole tiling. I'll show you the structure in the next slide. Okay, next slide. So this is sort of the elementary building blocks, but again, you still need to use overlap rules. So some of these clusters will sort of overlap. They will share, say, 1 platelet or some number of platelets. Okay, when actually put in the whole tiling. Again, what's important about this one is this is sort of the equilibrium rotational position. But again, if you rotate them, they will still be laterally bound. Okay, because these clusters actually turn out in the material at various angles. Okay, and this is something what breaks if you use just the degenerate planar anchoring. Okay, this is where things start to break. Okay. Okay, another way to think about, and here I'll give you a reference, okay, is to think about the Penrose tilings as decagonal clusters. It's another object, okay? Here again I show, and it turns out, again, this is stable. Okay, somehow you should visualize that this thing starts to hold together. Okay, starts to hold together, and again, it's stable in lateral direction, even if you rotate it at some other angle. Now, when you have this, you sort of see there are regions which will hold your tiling together. In particular, because you can imagine that I'll be able to hold tiling making this, putting the next one here, but they will overlap, so there will be sort of regions of net force, stress, which you can put different words that will hold your structure together. And actually, that's the structure of the largest structure we can make of a Penrose P1 tiling. There's really 176 particles in here. Okay, around them, it's a pneumatic liquid crystal. So in all the voids you see a pneumatic liquid crystal. This is sandwiched in a pneumatic cell. Okay, you have here at top view. And so really to convince you that that's a Penrose tiling, okay, that's a sheen. Okay, this is how Penrose tiling looks like. And this is Professor Penrose standing on the floor, which is the Penrose tiling. Okay, so this is the Penrose tiling structure. To be a bit more quantitative, so this is how the rector looks like in these regions, in these voids between the particles. And so here I show you just a potential. What happens if you sort of consider this breathing mode of the structure, right? Say that you try to expand it in every direction equally. Okay, you see how the free energy goes high, increases strongly. Okay, it's strongly bound. This is just one mode which you might think of. Okay, and now to give you this last idea. What these tilings might do, okay, I want to show you actually one could get hierarchy into these materials. What do I mean by hierarchy? Okay, you see the elementary building blocks of our tiling was a pentagon. Okay, was this pentagon? Actually, what you can do, you can replace the pentagon with 6 pentagons. Okay, of such and you can replace it in such a way that they exactly geometrically match. Huh? And actually, you can continue this process even further, and you can replace each of these guys with 6 smaller ones. And it works. And why it works is because you will remember that the potential between the particle, as soon as you have a potential which is based on nematic elasticity, it has no, people would say, internal scale. Okay? So even if you have particles of different size, okay? You just change the size of the particle. What changes is only the magnitude, roughly, okay? It works roughly, right? Changes only the magnitude, particularly if you're a bit further apart, okay? The magnitude and not the structure. And really, so this is just an example showing you the potential along some very distinct direction for these three particular sizes. Now, if you can do that, well, what I'd like to do is now to build a hierarchical tiling. Okay, this is a section of our Penrose tiling. And you see here, we want to replace one pentagon with smaller pentagons and further on. Actually, it turns out it works. This is an image from an actual numerical calculation. Okay, it works. So you really see, you can get, in this case, we managed to do 3 scales of particles in this material. And now sort of to give really sort of a photonics perspective on these structures, well, we have here particles of 3 scales. So in these 3 scales, what we're speculating about, okay? We haven't tried, we're doing it, okay? Is actually that the any optical response might come from the 3 scales. Actually, the length scale of this should correspond to the length, to the actual wavelength of the light. So we're trying to think about these materials to respond at 3 different, in this case, 3 hierarchical frequency regions, okay? With this, I'd like to conclude. So I hope I showed you 3 families of materials: 3D nematic colloids, blue phase colloid crystals, and Penrose P1 tilings. Okay, thank you for your attention.
Thank you very much. There is a little time for some questions. I see one there.
Just a short question. I think you mentioned that the colloid caused weak anchoring. Did you also try stronger anchoring? And yes, what was the effect?
So what can happen if you increase anchoring size? So if you want to speak in this language, so the particles start to feel one another. If you want, okay. So what can happen? You can also get distorted structures. So it's much easier for the particles to stick to one another. So you might lose the periodic structure. But though, if you initialize them in the right spots, they will stay there. But that's sort of the experimentalists. Will argue that this is quite artificial.
Yes. 2 more questions. And then you.
So for the FCC and the BCC colloidal crystals. So you talked about doing band gap engineering by putting quasi-crystalline order. Because these things form these crystals, there'll probably be dislocations in the colloidal lattice.
Okay, yeah, so I might immediately say this is one of the works which I think doesn't have this, right? This is the question, right? So, I mean, this is, I think, a work which is not realized yet, so there's no experimental counterpart to it yet. That's something I must say immediately, right? So I think I cannot give a full answer to this, sort of from the experimental perspective. We did try to think about what might be the problems. What can happen is that some of the sites might be overpopulated or underpopulated. So they might just be empty, or in some spots you might get too many particles. Okay, this is, I think, what happens. Now, to really get a dislocation in the system, of course, a dislocation can come from the phase itself. So the blue phase can form dislocations. This is known. So you can get dislocations in the system as well. Yeah.
But maybe even in the colloidal lattice, you could get loops going because it's a crystalline system.
True, but they're coupled. They're strongly coupled. Yeah, it's a good point. We're actually thinking about dislocations in blue phases. That's a separate work. I mean, it's a work in process. Yeah.
Okay, quickly, last question.
Last question. Your mesh size, you find a difference method, about 10 nanometer.
Sure.
As I understood. What was the colloidal lattice constant?
Colloidal.
Did you check it? The particle size also, the distance between these two particles is about 15 nanometer.
Not 15, it's more 50 or 100.
Yes.
It's 100, so it's, yeah. So we have 10 nanometer size. And so okay, to give you the example with smallest particles, okay, with largest one it works, okay? Okay, so this is 120 nanometers, okay? 120 nanometers, so you might say this is 12 mesh points, if you want to speak in mesh points units. And here, this is 50 mesh points. Thank you. Yeah, this is, and it works. I mean, the question is actually very relevant, because what might happen is that you get pinning of defects if your mesh solution is too small. We checked this. Yeah, it works. Yeah, we checked it. We are very careful about this. We are just at the border. If you go to set up resolution, sort of mesh size, say 30 nanometers, then I'm not sure anymore. Okay, we are very careful about this.
You will get the results, but results will be wrong.
Yes, exactly right. Exactly right.
Very well.
We are very careful about this.
Very well. Thank you very much again.